Well, we're going to discuss an LCR series circuit, which is an inductance, a capacitance, and a resistance combined in series. So here is a circuit that you see. You have an inductor, a capacitor, and a resistance with an alternating EMF connected. The arrow here represents the direction of the current through all three components. And the voltage across the resistance is always in phase with the current through it. Therefore, that's represented by this arrow now. And the voltage across the resistance is given by the product of the current and the resistance. So that is I times R. But the voltage across the inductor always leads the current by 90 degrees. So this is a vector rotated through 90 degrees in the counterclockwise direction. And it represents the voltage across the inductor. But the voltage across the capacitor lags the current by 90 degrees. So the green arrow represents the voltage across the capacitor. And the vectors are continuously rotating with an angular velocity omega. That's why I have this animation on the side to show that all three vectors are rotating, but they maintain the angular difference between them. And once again, I've drawn it on the right side to show the voltage across the resistance, the voltage across the inductance, which is I times XL, and then voltage across the capacitance, which is I times XC, where XC and XL are the capacitive and inductive reactance. And this now is the difference between VL and VC. So this is actually I XL minus XC. So that's actually the difference between the first vector and the second vector. And why do we do that? Because they are opposite to each other. That's how you find the resultant of two vectors when they are opposite to each other. And like I said, it is I XL minus XC. Now we got to find the resultant of this vector with IR. Now, in order to do that, we have to complete the parallelogram here and trace out the diagonal of this parallelogram. So when you trace out the diagonal, the length of that diagonal gives the magnitude, and the angle that it makes with the x-axis gives the direction. So that is going to be the resultant of all the three vectors. And in order to find this, you just have to square both sides, add them up, and take the square root, which is what I'm writing now. It's I, because square root of I squared is I, that's taken out, and R squared plus XL minus XC whole squared. So that is the resultant voltage. That is the net voltage or the resultant voltage in an LCR series circuit. I'm calling it the output voltage here, the net voltage, and that's once again I times square root of R squared plus XL minus XC whole squared. Now this factor here, which is a sum of a resistance and a reactance, is called the impedance, represented by the letter Z. So impedance is the sum of a resistance and a reactance, and in this case it's given by this formula, square root of R squared plus XL minus XC whole squared. So that's how you calculate the impedance in an LCR series circuit. We can also find this angle here, phi by just taking this triangle and taking tan phi. So tan phi is going to be opposite side by adjacent side. We know that the opposite side is I XL minus XC, and the adjacent side is I times R. The I's get cancelled, that's why I've not written them here. And so tan phi is XL minus XC by R. So that's how we find the angle. Remember that XL is omega times L, and XC is 1 by omega C. And both of these quantities are measured in ohms. They are called reactances, and their unit is ohms. So the voltage at any instant, V as a function of time, is V naught sine omega t, which is what we have here. But the current at any instant is given by I naught sine omega t minus phi, where this is phi. So the voltage and current are not in phase with each other. Generally, you could say I naught sine omega t plus or minus phi. So that's how the voltage and the currents are related. Now let us talk about resonance in an LCR circuit. Now for resonance to happen, the voltage across the inductance and the voltage across the capacitance have to be equal. We know that they're already opposite to each other, so if their magnitudes are equal, they will cancel out. And that is the condition for resonance. The voltage across the inductance should be equal to the voltage across the capacitance. And let us find out for what frequency this is going to happen. Because voltage across the inductance is IXL and voltage across the capacitance is IXC. So we can cancel out the I's, and then we know that XL is omega times the inductance, and XC is omega 1 by omega C. XC should be 1 by omega C, which will give us, okay. So from this we get omega is equal to 1 by root LC. And that is called the resonant angular frequency. If you draw a graph between omega and current, you see that for one particular frequency, omega naught, the current becomes maximum, as you can see. And that is the resonant frequency. And this is what we checked in the lab today, that for one particular frequency, the current becomes a maximum. That is called the resonant frequency. Get that? So at resonance, the impedance in the circuit is a minimum and the current is a maximum. So at resonance, impedance is minimum, current is maximum. And actually the impedance would just be equal to the resistance, because these two cancelled out. And the maximum current is given by the maximum voltage divided by the resistance. That's an important point. Again, at resonance, the impedance is simply resistance, because the reactances cancel out. All right, so that's what I've written here. And once again, impedance is given by this formula as we saw before. And when these two become equal, they cancel out, so you get a 0 here. And then when you take the square root of R squared, you get an R. So 3 important things. At resonance, the inductive reactance is equal to the capacitive reactance. That's number one. Current is maximum, impedance is minimum. That's number two. And number three, the total impedance of the circuit is simply the resistance of the circuit, which is its minimum value. So this is some very important information about LCR series circuits. I hope you understand this. Thank you.